Hello, my name is Mullikin, and I am a graduate student at Penn State University in the United States. The work I'm going to describe to you today concerns the possibility of the origin of life at hydrothermal vents involving metal sulfide catalysts, as well as coacervate droplets, which may act as prebiotic compartments. The premise for this idea is the well-accepted concept that compartmentalization is essential for prebiotic chemistry. In general, increasing the concentration of chemical reactants will increase reaction kinetics and speed up the rate of reaction. Compartmentalization is a way of decreasing volume and therefore increasing concentration, making reactions between prebiotic precursors, for example, more likely. Liquid-liquid phase separation, or liquid phase condensation, is one way of forming a compartment. If prebiotic precursors are dispersed throughout the entire early Earth ocean, it would be much too dilute for biochemistry-like reactions to be feasible. On the other hand, compartments like coacervates could sequester prebiotic molecules and gather a small volume of concentrated primordial soup. The coacervates that I'm interested in specifically are associative or complex coacervates, meaning that the constituents associate with each other through electrostatic interactions and form a dense polyelectrolyte-rich phase within a dilute aqueous phase. Due to the release of counterions when the two polyelectrolytes come together to form a complex, this process is entropy-driven and occurs spontaneously under the right conditions including pH, salt concentration, and temperature. Coacervates were first proposed as a player in the origins of life by Oparin in the early 20th century. Oparin noted the ability of coacervates to sequester molecules, which could then undergo reactions within the coacervate, and the ability of coacervates to increase in size. He compared these metabolism and growth-like properties to the protoplasm of modern cells, which is not a very good comparison and caused the idea of coacervates in origins of life scenarios to be discarded for a while. However, we now know that while coacervates are not similar to cell protoplasm, they are similar to biomolecular condensates or membraneless organelles. Also, there are features of coacervates which make them worthwhile to consider as players in the origins of life, including varying behavior in different environmental conditions like temperature or salt concentration, sequestration of biomolecules, and the ability to harness natural gradients and act as reaction and organizational compartments. Now we will return to the environment that this project is focused on, which is hydrothermal vents. The images here are from the lost city vents, which have moderate temperatures compared to white smoker and black smoker vents, which get up to hundreds of degrees Celsius. The reason the lost city vents are cooler is because they're off-axis, so the vent fluid does not come into direct contact with magma. In contrast to black smoker vents, which have acidic effluent, lost city vents are alkaline. Finally, the mineral composition of the chimneys is different, with lost city vents being ultramafic and mostly magnesium and iron olivine. These minerals undergo serpentinization and produce hydrogen gas. In contrast to the vent fluid, the early Earth ocean was cool and slightly acidic, containing dissolved CO2 and metal ions. One important feature of black smoker vents, in particular, is that they contain hydrogen sulfide in vent fluid, which can react with aqueous iron in the early Earth ocean to form iron sulfide minerals. In the late 80s, Vectorshauser proposed an iron-sulfur world hypothesis of the origins of life, where pyrite minerals catalyze prebiotic reactions and allow early biomolecules to arrange and associate on the mineral surfaces. The other feature of hydrothermal vent chimneys that is interesting for this project is pores, which you can see in this image, and they can be tens or hundreds of microns in diameter. These pores can facilitate reactions within small volumes, which mix through diffusion rather than turbulent mixing due to the geometry of the pores, and due to this also, a large amount of the fluid is in close proximity to the minerals that make up the pore walls and may catalyze reactions. Because of the pH, temperature, and solute differences between vent fluid and ocean fluid, these pores would also have pH, temperature, and chemical gradients that could provide energy for prebiotic reactions. The different aspects of this scenario are represented in this small diagram, where the acidic ocean fluid and alkaline vent fluid enter a microfluidic channel and travel with laminar flow. Reactants in the fluids undergo reactions catalyzed by the iron-sulfur minerals and may produce polypeptides, which can then form coacervates within the pores. The pores have pH and temperature gradients due to the different conditions of the ocean and vent fluids, which can further encourage reactions within the vent or within the coacervates there. The first aspect of this I'll focus on is the production of coacervate components. In order to look at the feasibility of producing these polypeptides in a hydrothermal vent setting, we return to the iron-sulfur world hypothesis of Vectorshauser and the iron-nickel sulfide cluster catalyzed peptide bond formation mechanism shown here. In the past, this mechanism has been tested mainly with glycine and phenylalanine, and starting with the simplest amino acid, glycine, we replicated the production of glycine dimers. The next step is to use arginine and aspartic acid. For the associative complex coacervates that I'm interested in, the constituents need to be oppositely charged so that they will interact electrostatically. Commonly, we work with a tenmer of a cationic amino acid, like arginine, and a tenmer of an anionic amino acid, like aspartic acid. Here you can see the different charge states of arginine, which has amine groups in its side chain and can have a maximum charge of +2. We work at a slightly basic pH, where it has a single positive charge. And then below you can see 4 different charge states of aspartic acid, which can have at most a net charge of -2, but at slightly basic pH it has a single negative charge. An interesting note for production of coacervate components is that the peptide bond formation mechanism that we are taking advantage of proceeds at the N-terminus of the amino acid. Since arginine has extra amine groups in its side chain compared to something like glycine, which only has a hydrogen instead of a true side chain, it may be possible for this reaction to form branched polypeptides with arginine. Although this would be undesirable if one were trying to produce biological peptides, since we're interested in polyelectrolytes for coacervate formation, this is an entirely good option for us. The next part of this research is an investigation into how polypeptide coacervates and iron-sulfur minerals interact. These microscope images are of equal charge ratios of arginine tenmer and aspartic acid tenmer with iron-sulfur mineral. The salt is relatively high to mimic ocean fluid, and the solutions were mixed under argon gas to replicate the anoxic conditions of early Earth. As you can see, the minerals seem to be encompassed within the coacervates. With higher mineral concentrations, this scenario changes so mineral structures dominate and the coacervates associate at the mineral surfaces. This is a particularly interesting result for the next part of the project, which is microfluidics. An important part of the environment that we envision these interactions taking place in is the micron-scale pores of the hydrothermal vents. To replicate and study this in the lab, we are using microfluidics. Currently, we use simple Y-shaped channels. From one inlet, we introduce the acidic, ocean-like fluid containing iron-2 cations and the cationic coacervate constituent, which is arginine tenmer. And from the other inlet, we introduce the alkaline vent-like fluid containing sulfur anions and the anionic coacervate constituent, which is aspartic acid tenmer. The microfluidic devices are made of PDMS, and solutions are flowed through using a syringe pump. Due to the fluid dynamics in micron-scale channels, there is laminar flow, which is important for us because the solutions will only mix by diffusion rather than turbulent mixing. Because of the charge on the PDMS wall and the parabolic nature of the flow speeds in such a channel, charged species will be somewhat more concentrated at the walls. Also, as the iron and sulfur ions happen to meet at the fluid interface at the center of the channel, a metal membrane forms at the interface of the two solutions. This will also be charged and will divide the channel into two again, creating two new parabolic flows and concentration patterns. Because of the different pHs of the two solutions, a pH gradient should form. To get really close to what might happen in hydrothermal vent pores, I also intend to design a device with a temperature gradient, where the ocean fluid is cold and the vent fluid is warm. As for coacervates, if the fluorescence microscopy results I showed earlier are any indication, the coacervates should also stick to that membrane and become a location for other interesting molecules such as RNA in solution to accumulate near a mineral catalyst. Currently, we are working on protocols to keep samples anoxic for study with confocal microscopy, Raman microscopy, X-ray diffraction, and scanning electron microscopy to understand how the coacervate constituents and minerals interact in micron-scale channels. Moving forward with this project, the first aim is to produce charged polyelectrolytes through the iron-sulfur mineral catalyzed peptide bond formation, particularly using arginine and aspartic acid. With both bulk and microfluidic experiments, we need to characterize the iron sulfide minerals that are forming and determine their actual surface properties such as charge and catalytic activity. Part of the difficulty of this step is maintaining anoxic conditions, since iron sulfides will quickly oxidize to iron oxides and hydroxides under ambient atmospheric conditions. Knowing the surface charge of the mineral particles or clusters, we can then change the charge ratios of the polycations and anions that make up the coacervates to manipulate how the coacervates wet to the minerals. Finally, in the microfluidic system, we will introduce and monitor pH, redox, and thermal gradients to more closely mimic hydrothermal vent pores and introduce prebiotic and biotic molecules like RNA to see how these conditions, combined with the presence of coacervate compartments, can create a type of functional system. I'd like to conclude by returning to the bigger picture of how coacervates can be an important piece of the origins of life at hydrothermal vents. Their ability to respond to environmental conditions and sequester specific prebiotic molecules allows for something akin to a selection process, or at least transient processes involving uptake and release. By becoming enriched in biotic precursors and by associating and interacting with mineral catalysts like pyrite, they can enhance reaction rates. By associating with minerals in hydrothermal vents particularly, these coacervates could prevent the escape of prebiotic reaction products into the dilute ocean and also take advantage of pH, redox, and temperature gradients found in vent pores. Coacervates may well have been one form of an early protocell within a larger system of prebiotic chemistry, co-evolving with biomolecules like peptides and RNA. Of course, none of this work would be possible without support from the Keating Group and the House Group at Penn State, and I particularly want to acknowledge Sehun Che and Andrew Hyde for their direct involvement with the work presented here. At this time, I'll be happy to take any questions.